Happy Monday, everybody. Today we'll be taking Cornell Notes on converting decimals to fractions. So please put in an entry into your table of contents. It should be under the one about fractions to decimals, which we took last week. So this will be the reverse topic, decimals to fractions. Today's date is September 29, 2025. Feel free to take breaks throughout this video because this is going to be a longer one. You probably saw the time on this. But you will need about 2 or 3 pages of notes for this because we'll be creating some prime factorization tables, and that takes up a lot of space on your paper. So come prepared with enough paper to take notes. And yeah, feel free to, again, to pause whenever you have to. Okay. So please set up your papers Cornell style. Make sure that you have your objective on the top. Our objective today is I can identify different types of decimals and convert them into fractions. On your left side, you should write the following terms, which we'll go over, and then right side again are definitions and examples. So the first term that we'll talk about today is a terminating decimal. This is a decimal that has an exact number of decimal place values. So we'll go over some popular ones. For example, we have the fraction 1/2, that if we were to take this and do long division with it, it wouldn't be very long because we'd stop at 0.5 or 0.50, right? There's just one place value after the decimal and it stops. Division no longer needed, we can stop there. So it terminates or ends there, right? That's what terminating or ending means. It's an ending decimal, no need to divide forever and ever. Another really popular one, 1/4, which turns into 0.25. And we'll stop there, right? Even if we were to set this up as a division problem, the division wouldn't be super long because we'd stop after we get to 5 in 25. Or even another one is 1/8, which turns into 0.125. And it stops there. It's a bit longer than 1/2 and 1/4, but it stops, right? After 5, we'd stop there and we get a 0 at the bottom of our division. It's ending, therefore it's called a terminating decimal. But there are a lot of examples of non-terminating decimals, and these are decimals that we can divide forever and ever and ever and never have a complete 0 at the bottom of our long division. And we'll go over some examples of that. One example that we actually went over together was 1/7. So we'll do the division here. Top dog in the doghouse, I put 1 on the inside and 7 on the outside. I turned this 1 into $1 and I put my 0 and decimal point over. I asked myself how many times does 7 fit into 10? Fits in 1. 1 times 7 is 7. I subtract 7 from 10. 10 minus 7 is 3. I drop down my 0. 7 fits into 30 4 times. 4 times 7 is 28. 30 minus 28 is 2. I bring down a 0 because I don't have a 0 at the bottom yet, so I have to keep bringing zeros down. 7 fits into 20 2 times. 2 times 7 is 14. 20 minus 14 is 6. Bring down another 0. 7 fits into 60 8 times. 8 times 7 is 56. I subtract 56. And I'm still not getting a 0. And actually, because I could go on forever and ever and ever and keep dividing, and I'm never going to get a 0 at the bottom. So I'm going to tap out there because I don't have all day. And I can put ... to symbolize that this actually is a non-terminating decimal because it doesn't end. Even if you put it into a calculator, you're going to see a bunch of digits, but it's only showing you the ones that it can fit into the screen. It actually goes on forever. There are other types of non-terminating decimals, a specific kind, which are repeating decimals. And we'll go over some examples as well. For example, one popular one is 1/3, which turns into 0.3333, and I can write this all day, right? But because we don't have all day, we would write that as 0.33 with a dash over the 3. So that's a repeating decimal. Another super cool trick about our ninths are that they're all repeating decimals. So 1/9 turns into 0.1111 repeating. So I would write that as 0.11 dash over 1. 2/9, same thing, 0.2222 forever and ever and ever. So this would be written as 0.22 dash over the 2. Another one, 3 over 9, which simplified is actually 1/3 if I divide both top and bottom by 3, which is, like we went over, 0.3333, which I can write as 0.33. And if we were to do 4 over 9, yep, you guessed it, 0.444 forever and ever and ever, which we could write as 0.44. So that's something you should keep in your back pocket about ninths. Shortcut, you should know that it's the numerator repeated itself, right? But repeating decimals don't necessarily have to have all the digits the same. It could be like something like 0.272727. 27 is being repeated, so that's also a repeating decimal. Or it could even have an initial different digit like 0.811111. This is still considered a repeating decimal because 1 is repeating, but 8 stays a little different, and it's fine, right? We would write that as 0.811 repeats itself. Okay, so those are examples of repeating decimals. But on to what we really want to talk about today, which is how to convert a decimal into a fraction. So we can turn any decimal at all into a fraction as long as we know their place values. But if you don't know that, that's also totally fine, because there's just a few general rules that we could follow, or patterns that will help us to convert any decimal into a fraction. For example, let's say I have 0.12. Okay, so what I would do is take my digits after my decimal, in this case it's 12, and I would put that into a numerator. So I'm going to write that in my numerator, 12. And my denominator is going to start with 1, and depending on how many place values there are after the decimal is how many zeros I'll have. So this has 1, 2, so I'll have 1, 2 zeros. So this is the same as 12 hundredths, which makes sense, right? This is 12 hundredths is in the hundredths place. The 2 is in the hundredths place. So this is 12 hundredths. Another example is, let's say, 0.345. Okay. Same thing. I'll take my digits after my decimal place, which is 345. So that'll be my numerator, 345. And my denominator will start with 1, and depending on how many place values I have after the decimal, 1, 2, 3, will be how many zeros I have after my 1. 1, 2, 3. So this is 345 thousandths. And it makes sense because this 5 here is in the thousandths place. Cool. This can also apply even if there's only one digit after the decimal, like 0.8. Okay. We can also turn that, take the digit after the decimal, which is 8. So I'll put that as my numerator. My denominator will start with 1, and we'll have only 1 0. So that's 8 tenths. Cool. And just to make sure everything is clear, let's say I have 4.56, right? I'm going to split this off into 4 and 0.56. If I add those two together, I would get 4.56. And then I'm going to write this as 4 and 56 as my numerator, and 1 1 and 2 zeros. Okay, so that's 56 hundredths. Cool. All right. Moving on to then simplifying fractions. So all of these fractions could actually be further simplified. None of these are actually in their simplest form. And what I mean by simplest form is taking a fraction and dividing it down all the way until there are no longer any common factors between them. So there are a couple different strategies for simplifying fractions. So you might want to take a moment to write that section down. But let's take, for example, the fraction 6 over 12, right? So we'll talk about the strategy dividing down now. dividing down. So if you're not super familiar with the factors of a number, then you can just begin by asking yourself, are these numbers even? If so, then I can divide by 2. And we can start there, right? Taking baby steps, dividing both the top and the bottom by 2. 6 is divisible by 2, 12 is divisible by 2. And when I divide that, I get 3 over 6. Cool. And then I have 3 over 6. 3 is not an even number, but 6 is. So I can't divide by 2 because that's not a common factor that they have, but I can divide by 3. So I can divide both the top and bottom by 3. And 3 divided by 3 gives me 1. 6 divided by 3 gives me 2. So 6 over 12 is actually the same as 1/2. Right? Let's say we have a slightly larger number. For example, 24 and 48. Same idea. We can actually continue to divide down. Both of these numbers are even, so I can just start by dividing by 2. And top and bottom divide by 2. And 24 divided by 2 is 12. 48 divided by 2 is 24. I once again have even numbers on the top and bottom, so I can divide both the top and the bottom by 2. 12 divided by 2 is 6. 24 divided by 2 is 12. And I can continue to divide by 2. 6 and 12 are both divisible by 2. And we have the fractions that we started with, right? 3 and 6. And both of these are divisible by 3. And I would get 1/2. So all of these fractions are actually equal to each other, but only this one is the simplest form, right? So we can take baby steps and just divide by what we think this is even, so we can divide both of them by 2 and on 2 and 3 in this case. Notice that all of these are also just prime numbers. And also notice that they're the same at the top and the bottom. So I can't mismatch. If I divide the top by 2, it has to be the bottom also has to be divided by 2. So I can't mix around the number like that. But if you're a little more familiar with the multiples or the factors of numbers, then you can just skip to straight up dividing by common factor, the greatest common factor. Dividing by, and there's an abbreviation for that, greatest common factor. And we'll take 24 and 48 as an example. 24, 48. Cool. And we can list out all the factors of 24, which are 1 times 24, and then 2 times 12, 3 times 8, 4 times 6, 6, 8, 12, 24. These are all the factors, because if I multiply 1 times 24, I get 24. 2 times 12, I get 24. 3 times 6, I get 24. Sorry, not 3 times 6. 3 times 8, I get 24. And 4 times 6, I get 24. Right? So those are all the different combinations of numbers I can multiply together to get 24. And same with 48. I can, wow, this is going to be a longer one. This is going to be 1, 2, 3, 4, 6, 8, 12, 24. I think that 48. Was that it? That might be it. And I, once again, 1 times 48, 2 times 24, 3 times 12, 4 times, no, not 3 times 12. Wait a minute. 3 times not 12, but 4 times 12, 6 times 8, and 48 divided by 3 is 19. So 19 would also fit here. 3 times 19, right? So those are all the multiples of, factors of 48. So now I want to double check which of these are in common. So I have 1, 2, 3, 4, 6, 8, 12, 24 in common, with the greatest one being 24. So this is the greatest in both of them. So I can just skip to straight up dividing by 24 on both top and bottom. 24 divided by 24 is 1, and 48 divided by 24 is 2. And wow, see, we just skipped the dividing part into basically just dividing straight up by the greatest common factor instead of dividing by 2 and then 2 and then 2 and then 3, which if we multiply together would actually give us 24, just so you know. Which brings us to our last method, and this one is actually one of my favorite methods of simplifying fractions. It will seem a little ridiculous at first because it's really long, but it's called prime factorization. And this is, for example, when we have larger fractions where maybe we're not too familiar with the factors of that number. So we'll start off with smaller examples and then we'll go over a larger example. Let's take 24 over 54, right? If I wanted to simplify that fraction, I don't necessarily know what the greatest common multiple between them are, or maybe I do. But what I can do is take both of these numbers, both of them, and I'm gonna set them up with a little space between them because I'm gonna do separate things with them. I'm gonna do what's called prime factorization tree, and I'm gonna split this up into all of its factors. So it's prime factors. So 24, I know I can make 24 by multiplying together like 6 and 4. And I can make up 6 and 4, or I can make up 6 by multiplying 3 and 2, and I can make up 4 by multiplying 2 by 2. And I can't further break these numbers down because these are prime numbers, right? So I can rewrite 24 as, and I'm going to write them from smallest to greatest. So 2 times 2 times 2 times 3, right? And you could double check that on a or on a calculator if you need to. 2 times 2 times 2 times 3 will be 24, right? So I just broke down 24 into its prime factors, and I could do the same with 54. So I know 54 is the same as 9 times 6, and I could break those further down because these aren't prime numbers. So 9 and 6, 9 I could break down into 3 and 3, and that's a prime number, and this is also a prime number. And then 6 I can break down into 3 and 2, and these are prime numbers. So again, I'll write this in from least to greatest. 2 times 3 times 3 times 3, and that would be 54. Okay, so I just broke it down into its factors, more specifically its prime factors, right? So my numerator here, 2 times 2 times 2 times 3 is 24. My denominator here, 2 times 3 times 3 times 3 is 54. And I can cancel the ones that I have in common. So on the top here, I have a 2 and a 2, so I can cancel those. And over here, on my right side, I have my 3 and my 3, so I can cancel those because they're in common. But as my numerator, I have 2 times 2, and as my denominator, I have a 3 times 3, and those are not overlapping numbers. So I can take those two and just keep them, multiply them back together. 2 times 2 is 4, and 3 times 3 is 9. So this fraction in its simplest form is actually 4 over 9. Now that was like super complicated and long. Maybe you would have noticed that both of these are just divisible by 6 and just straight up cut to that. Divide both the top and the bottom by 6 and you would have gotten 4 over 9. Cool. But taking a look at what we just learned, turning decimals into fractions, let's say I had a decimal like 0.0 375. Okay. Now I'm an expert at turning this into fractions now. So I will take my numerator and it will be the digits after my decimal, which is 375. And my denominator is going to start with 1, and I'll have 1, 2, 3 zeros. 1, 2, 3 zeros. Right? Now, if I'm being asked to simplify this fraction, I don't have a clue what the greatest common factor between them is, because I actually don't have my factors of 375 memorized. It's like not on the multiplication chart that I've learned from. So this is where I would use a prime factorization, where I would just take baby steps and break down the number into to the smallest forms, which are its prime factors, and then cancel out both the top and bottoms, whichever that they have in common. So we'll just go straight into solving that. So once again, I'm going to give myself some space, 375 on my left side, 1000 on my right side. And I'm going to create my prime factorization tree of 375. First of all, it's an odd number because it's ending in an odd number. So it's not divisible by 2. But if it's ending in 5 or 0, it is going to be divisible by 5. So I'm going to split this up into 5 and 75. Okay. And I did division beforehand, so that's why I knew that 5 times 75 is 375. Then I'm going to break this 75 further because that's not a prime number, but 5 is. 5 is already prime, so I don't need to break that down. But 75 is the product of 3 and 25. Now, a cool trick, you don't have to remember this, but if you want to know if a number is divisible by 3, you can add up its digits, like 7 plus 5 here is 12, and 12 is divisible by 3, so I know that this whole number is divisible by 3. Just a little tip, you don't have to remember that, but if you do, super cool. So 75 I know is divisible by 3 because 7 plus 5 is 12, and 12 is divisible by 3. But also because I know that 25 quarters give me 75 cents, so that's just also common. It's just something I know. Okay, and then 25 can be divided by 5 and 5. And now all of these are prime numbers. So 375 is the same as 3 right here times 5 times 5 times 5. And I would write that all as a numerator here. 3 times 5 times 5 times 5. Now moving on to 1000, which feels like a heavy number. It's a pretty big one. I'll just start off by dividing it by 2. I know it's an even number. So that's 502. And then if 500 is further divisible, if I cut that in half, that's 250 and 2. And 250 is also divisible by 2. So I can count that by 2 and 125. 125 and 2 is 250. Now 125 is no longer divisible by 2. 5 is an odd number. So I'll break this down into 5 and 25. Okay, because 25 times 5 is 125. Or if I have 5 quarters, I have $1.25, so I could just scale up. And then 5 times 5 will give me 25. So here are all the primes that composed, if I multiply together, will create 1000. And I'll write them from least to greatest. So I have 2 times 2 times 2 times 5 times 5 times 5. Wow. So I can cancel anything that I have overlapping, which I have 5 and 5 here. I'll cancel this. 5 and 5 here. I have 5 and 5 here. I have 5 and 5 here. So I've gotten rid of all of my 5s now. Now I'm left with a 3, a 2, a 2, and a 2. So that's what I'm left with. That's no longer, there's nothing to cancel them with because they're not overlapping. So I'll then just multiply them back together. 3 times nothing else just stays as 3. And 2 times 2 times 2 is 8. So 0.375 converted into a fraction is 375 thousandths. Simplified is actually just 3/8. That crazy. And I found that out by doing prime factorization. So those are our 3 methods of um, simplifying fractions. Whatever works for you is fine, as long as you're able to bring a fraction like this into its smallest form like that.